Good afternoon and welcome everybody. Thanks for joining us this afternoon. We have three excellent speakers joining us today who I'm going to introduce shortly. And as people are continuing to join the meeting, I will go through our online housekeeping. So this meeting is taking place via a webinar, and if you look at the top left of your screen, you should see the small green shield, which indicates that you're using the most up-to-date version of Zoom and that it is secure. I also need to advise you that this meeting is being recorded. So as always, questions can be asked at the end of each presentation, but because you will be muted, please can you use the Q&A facility found at the bottom of your screen, and your questions will go to the panelists. And the questions today will be read out by the editor of A&G, Dr. Sue Bowler. So before our presentations, I just have a couple of announcements this afternoon. So the first one is regarding the AGM. So the 202nd annual general meeting of the Society will take place at 4 o'clock on Friday, the 13th of May, 2022. The second announcement is regarding NAM 2022. And in this year, the NAM meeting will be held in the University of Warwick from Monday, the 11th of July to Friday, the 15th of July. The abstract submissions are now open and will remain open until the 14th of April. And the conference registration will also open shortly. The third item is relating to voting in the RAS Council elections. So voting for the RAS Council elections will begin on the 12th of April and will be done electronically. And voting will close at midday on the 12th of May. The next announcement is related to some awards deadlines. You are now invited to send nominations for RAS medals and prizes to be awarded in January 2023. The deadline for nominations is the 31st of July 2022, with the exception of the Education Awards and the Annie Maunder Medal for Outreach, and those awards and medals have a deadline of Friday, the 30th of September. A couple of reminders then, there is still time to nominate for the Patricia Tompkins Undergraduate Prize, and the deadline for that is the 31st of May. So please do visit the RAS website for more information. The second reminder is that the deadline for the Caroline Herschel Prize Lectureship is the 30th of April. So please visit the William Herschel Society website to complete an online application. Okay, so on with the main programme for this afternoon. So first of all, we're going to hear from Dr. Richard Morton from the University of Northumbria, who is the recipient of the Fowler Award G for 2022. So Dr. Richard Morton is currently an Associate Professor at Northumbria University, working in the Solar Physics and Space Research Group. He is a UKRI Future Leaders Fellow, and his research focuses on investigating magnetohydrodynamic wave propagation in the sun's atmosphere. Richard is also active in STEM public engagement and is the public engagement lead on a European-wide Horizon 2020 research infrastructure project called SolarNet. So welcome, Dr. Richard Morton, to the meeting. I'm looking forward to your presentation, which is entitled Revealing the Hidden Corona with Infrared. So I'm going to hand over to you, Richard, so that you can share your slides and begin your presentation. Thank you.
Good afternoon, everybody. It's great to be here with you today, and I'd like to thank the RAS for inviting me to give a presentation. And what I'd like to talk to you today about is my work on wave propagation in the sun's atmosphere, and predominantly how we've looked at waves in the corona with the infrared, or in the infrared. To start, though, I wanted to provide a bit of context and a bit of history around solar observations that I thought were sort of good for setting the scene. So this image is of an eclipse taken back in 2008. So the sun is obscured by the moon here, which has been blacked out. And I like this image a lot because each of the elements that make up this image has a lot of significance in terms of the history of observations of the corona. So the corona was first identified in eclipse observations from white light emission, which can be seen as the greyish light around the moon. And it had been known, the corona had been known for many centuries. However, in the 1850s, when a new instrument called the spectroscope had been invented, it was pointed at the corona by two scientists called Young and Harkness. And they discovered something interesting. They discovered two emission lines in the optical, one in the green at about 530 nanometers and one in the red at about 790 nanometers. So there were these two emission lines that they didn't know where they came from, and there was no known elements that would produce these. It took around 70 years for this mystery to be solved. And in the time between, it was proposed that there might even be a new element in the sun's corona called coronium, which could explain these emission lines. However, in the 1930s, two astronomers, a German called Groschen and a Swede called Edelin, were very interested in the spectral line emission from the corona, and they were interested in looking at highly ionized ion atoms and the spectral lines from these atoms. And they managed to identify these green and red lines in the corona with emission from highly ionized ion atoms and forbidden transitions within those lines. Really, as a side note in their paper, they said that for these lines to appear, the corona had to have a temperature of about 1,000,000 degrees, but they didn't focus on it too much. And this idea of a hot corona was really taken forward by Hans Alfvénic in a paper about 2 years later. So he pressed the fact about the corona and how it should have a temperature of about 1,000,000 degrees. And after this initial realization of this hot corona, we still don't understand yet exactly how the corona reaches these temperatures. The mechanisms that are responsible for the coronal heating are still sort of a bit of a mystery. The other contribution in this eclipse image that will be of interest is the blue color, which you can't quite make out in this image, but it belongs to an ion line in the infrared at 1074. And I'll be talking about this line in a bit more detail later because I've used this line a lot for my research. So with the realization of a hot corona, it was quickly realized that there should also be emission from the corona in EUV and X-ray. However, we can't observe these wavelengths from the ground due to atmospheric absorption. So we had to launch space-based observatories. And the first solar observatory in space was actually on board a NASA space station called Skylab, so a very early space station. And they took up EUV and X-ray images. And this is a movie from the Skylab data taken in the 70s. And I think it has a very characteristic 70s feel, this movie. If you remember sort of programs from the 70s where you have very jerky images of space objects like this, it reminds me much of that. Skylab made many interesting discoveries while it was up there. What it was able to first identify was these dark patches, which were called coronal holes. It also saw magnetic loops for the first time in the sun's corona. And it also discovered these sort of short-lived bright emission patches called coronal bright points, as well as making many other fantastic discoveries from these first observations. To date, in space, we have we've had regular observations of the sun's corona from space since then. And I just wanted to show these two images from some more recent spacecraft. The first one is this X-ray image that comes from the Hinode satellite. So Hinode could actually observe the corona across many wavelengths, but in particular, it provided these sort of full disk X-ray images. And the other image I show shows the, I think, corona in beautiful detail. It's from the workhorse of solar physics observatories, the Solar Dynamic Observatory. And SDO has been up since 2010, and it's taken a 17 megapixel image of the sun's corona every second for the last 11 years in EUV. So we've really got a fantastic wealth of space-based data for us to be able to probe the dynamics and the heating of the sun's atmosphere. And it's kind of surprising that the progress still eludes us to the coronal heating mechanism. Closely related to this coronal heating mystery is the solar wind. So back in the 1950s, a British mathematician called Chapman realized that if the sun was, 1,000,000 degrees, or the corona was 1,000,000 degrees, then it must be an extremely efficient conductor, and there must be a flow of material outward from the sun that extended well beyond Earth and into planetary space. Around a similar time, it was also seen in observations of comets that the tail of the comets was always pointing away from the sun. with some suggestion that it could be some flow from the sun that caused this. It took Eugene Parker, a very famous solar physicist who recently passed away, to realize that there must be a wind that escaped from the sun. And Parker showed that the wind could actually be supersonic, reach supersonic speeds. So what I show here is some data from spacecraft that was sent up to measure solar wind. So this is in situ measurements. On the bottom, I'm just showing an indicator of magnetic activity in the sun's atmosphere. So this is represented by the sunspot number. And in the top plots, there is a X-ray picture of the sun, and the wind speed is plotted in these sort of contours. And what this spacecraft found, Ulysses, was that during periods of quite low solar activity, the solar wind had this relatively homogeneous structure. So very fast wind speeds at the pole, reaching speeds of 700 kilometers per second. So much faster than the sound speed and what was predicted by the Parker model, and the much slower speeds towards the equator. However, as magnetic activity increases, you can see there's these mixing of slow and fast speeds, wind streams, making a much more complicated pattern. So the mystery surrounding the solar wind is, how is the solar wind accelerated to these fantastic speeds? Right, so this is much greater than what was predicted by Parker. And it really needs some additional source of momentum in there. And it turns out the addition of momentum and the heating of the corona are kind of a related puzzle, or they appear to be anyway, at least. Okay, so we've seen that the magnetic field is important in the solar wind measurements. And if you think back to that eclipse image, we saw that beautiful structure around the corona. And that was due to the sun's magnetic field. So the magnetic field plays a key role in structuring the corona and also the solar wind. But it's also closely related to the heating of the sun. So on the left here, I'm just showing a magnetogram that's taken in the optical with an iron 1 line, and it shows the Zeeman splitting of that iron 1 line in the photosphere of the sun. And where you see these black and white patches, this is where we have the most intense magnetic activity. And you can see there's much smaller patches of magnetic field away from these intense regions as well. But if you focus on the intense regions and then sort of track your eyes over to the EUV image, also from the Solar Dynamic Observatory, shown on the right, you can see that there are these loop-like structures in the corona. And these loop-like structures are very bright, they're very dynamic, and it appears there's lots of heating because you can see this excess radiation. So as well as structuring the corona, the magnetic field is also intimately linked to the heating processes that are thought to go on there. So there is a real need for us to understand the coronal magnetic fields, but it turns out it's very difficult to measure this magnetic field in the corona. So unfortunately, we can't launch spectropolarimeters into space that are sensitive enough to measure the coronal magnetic field. This is because the coronal magnetic field is weak. So in that magnetogram image I showed you, that was able to measure the Zeeman splitting for fields of about 1,000 Gauss or above. Whereas in the corona, the field strength in general is expected to be less than 10 Gauss. And this leads to kind of negligible Zeeman splitting. So you need a very sensitive instrument to be able to do it. If we want to do it from Earth, we're still met with many challenges. So if we try and do it in the optical, we don't have enough Zeeman splitting. And if we try and do it in the infrared, it's possible, but then we suffer from lack of photons, atmospheric seeing, and all these additional complications, which mean it's very difficult to measure the coronal magnetic field, except in the most intense regions. The other reason that we need to measure the coronal magnetic field is shown in this image or this movie. So what we see is a solar active region, and we see flaring going off. We also see a prominence or two prominences here, and there's this kind of sympathetic relationship between the two. So once the flare goes off in this region, you see that we also have the liftoff of this prominence, and it also leads to a change in the coronal magnetic field that also leads to this prominence eventually taking off. So solar flares and prominences are related to, they're the drivers of space weather events here at Earth. And really, to be able to forecast or predict these space weather events, we need to understand the coronal magnetic field as well. So it's kind of an important thing that we can't really get access to from, say, traditional methods. And I'll discuss how an alternative way we can do this. So typically, solar observations from the Earth have been done in the visible. And this is because the Earth's atmosphere is opaque, is transparent to these wavelengths. So this plot here just shows atmospheric absorption as a function of wavelength. So you can see there's very little atmospheric absorption in the visible, but as we go to X-ray and ultraviolet, they're kind of completely blocked out by the Earth's atmosphere. And then we have these various windows in the infrared where we can take a peek at the sun's atmosphere from the ground. Predominantly, solar physics is focused on the visible because we have lots of photons coming from the sun in that wavelength. So we get some fantastic observations there. But really, if we want to study the corona, we need to move to the infrared and look through these atmospheric windows. The advantages of this are you have less continuum emission, so less sort of contamination when you do coronagraphic measurements. You also have less atmospheric and instrumental scattering in these types of observations, and you get an increased Zeeman resolution if you do want, or if you are trying to make magnetic field measurements. However, the downside is we have fewer photons coming from the sun at these wavelengths, and there are also fewer absorption lines or emission lines to choose from to make these measurements. So it's kind of a balance, really, to observe the corona in this way. One of the main instruments, or an instrument that has made a lot of measurements of the corona in the infrared, is located at Mauna Loa Solar Observatory. So this is an observatory located on Mauna Loa in Hawaii. It looks a bit like someone's shed, a bit of a tin pot observatory, but it's provided a lot of fantastic measurements over the years, so don't be fooled by the building. The other strange thing about this image is you can't see the sky in this one. So this happens to be one of the only days on Hawaii where it's cloudy when this photo was taken, so I believe. This observatory contains an instrument called the Coronal Multi-Channel Polarimeter. So this is a coronographic spectropolarimeter, and you can see the telescope poking out of the observatory here. And this COMP instrument is operated by the High Altitude Observatory, who are predominantly based in Boulder in the USA. And COMP makes measurements of the corona in these infrared lines. So in this 1074 nanometer line that I was mentioned back in those eclipse observations. And this can see the corona at iron 13, so roughly the temperature of 1.3 megakelvin. And COMP also observes this line at around about 1080 nanometers as well. So COMP was initially designed to try and make spectropolarimetric measurements of the coronal magnetic fields. But by sort of a bizarre twist of fate, it ended up making a fantastic discovery. And that is, it found the presence of MHD, or Alphanic waves, sorry, in the sun's atmosphere. So MHD waves had long been predicted by, I think Hans Alfvénic was one of the first people to discuss MHD waves. And we've seen them, we've seen the other varieties of MHD waves, sort of slow and fast waves elsewhere in the sun's atmosphere. But Alphan waves, which are highly incompressible waves driven by magnetic tension, they're very difficult to see, mainly because of the incompressibility aspect. But as part of COMP's setup, it was able to measure Doppler velocity of this infrared line. And it was in these Doppler velocity measurements that they found signatures of these elusive Alphan waves. So this was back in 2007. We had the first observations of Alphan waves in the sun's corona. And this movie just shows the Doppler velocities from the COMP instruments. And what you can see everywhere is there's sort of an upward flowing pattern from the occulting disk into the sun's corona. And you can see it's hopefully you can see it's kind of quasi-periodic pattern. You can get a better view of this signal if you, say, take a portion of this, say along this coronal loop here, and you take a Fourier transform of this. So the Fourier transform provides a frequency wave number power spectrum, which allows us to probe the waves. And you can see this very typical signature, this star shape pattern in these power spectra. And the slope of the arms of this star shape show the speed that these waves are moving at. And you can find that the speed is about 600 kilometers per second. And this is much faster than the sound speed in the corona. And this is one of the key clues that this was an Alphan wave or an Alphanic wave. No. So the reason we're interested in Alphan waves is because they're a key component of heating the sun's atmosphere. So they're one of the leading candidates for explaining the coronal heating problem. And so I just want to give you a brief overview of how this Alphan wave or Alphanic wave heating works. So here I have an image of the lower solar atmosphere. So this is taken in a molecular line in the continuum, and it's from the Swedish Solar Telescope. And what you can see is the granulation pattern on the sun's surface. But in the lanes between the granules, you see these bright features, and these bright features are the signatures of intense magnetic fields that exist in the photosphere. These magnetic fields expand up into the sun's atmosphere, reaching into the corona and beyond. But the key thing is that the convection actually excites waves. So there's a lot of energy in the convection, and it can excite various MHD waves. And one of these is these alpha modes, which is shown by this transverse swaying motion in this simulation. So these colored contours here just show temperature in the convection, and we have our magnetic field embedded in that convection region. And you can see it swaying the magnetic field, exciting these Alphanic waves. The waves, because they're incompressible, can then propagate upwards along the magnetic fields, not feeling much damping, and make it out into the corona and solar wind. So to be able to dissipate them, it turns out it's reasonably difficult, as I mentioned. But the key, or the leading theory in terms of wave dissipation, is based on Alphanic wave turbulence. So some of you may have experience with fluid turbulence. And what happens in fluid turbulence is you inject energy at a certain spatial scale, and eddies and vortices form in the fluid, and they break that energy down. And the energy is broken to smaller and smaller spatial scales, where eventually it's dissipated. Now, in a fluid, this is isotropic, and it happens the same in every direction. But actually, in a plasma, where you have a magnetic field, you introduce a preferred direction. And this cascade of energy is actually suppressed along the magnetic field direction. So you predominantly get the cascade perpendicular to the magnetic field. And that's kind of the key difference in Alphanic wave turbulence. So there are many successful models that show this kind of alpha wave type heating can produce a heated corona. And this is just an example of one of those. So we have a magnetic field that's driven at the photosphere by alpha waves. And in this case, the alpha wave is a twisting motion. And it causes the field, or the magnetic field, to become turbulent in the corona, and you end up with wave dissipation. So that discovery of alpha waves was kind of key for supporting these theories of alpha wave turbulence. However, that picture that I outlined of alpha wave propagation and driven by the granulation doesn't quite fit the observations. And this is the focus of some of my recent work. So here, instead of showing that two-dimensional power spectrum that I showed before of the waves, I'm showing just a one-dimensional power spectrum that is now frequency against power. And what appears in this power spectrum is this bump around about 4 millihertz. And this bump appears everywhere through the corona. It appears to be present, whenever we look. And it's not expected from this granulation-driven picture of alpha waves. So it's suggesting there's another source of alpha waves in the sun's corona. And this can come about through a sort of slightly complicated mechanism of mode conversion. And it all starts off with the acoustic modes in the sun's interior. So the acoustic modes are driven by the subsurface convection. They spend a long time bouncing around the sun, and they're the ones that have been used for helioseismology and astroseismology as well. It turns out these acoustic modes, or P modes, as they're known, can leak out from the interior along these magnetic fields. So these magnetic fields provide what are called magnetoacoustic portals, allowing the P modes to come into the sun's atmosphere. And once they do, they are able to mode convert. So they start off as fast acoustic waves in the interior, they mode convert to slow and fast waves at some height in the sun's atmosphere, where the sound and the Alphen speed are equal. And then the fast waves from this process are then able to mode convert close to the sun's corona, producing Alphen waves. So the peak of the P-mode power spectrum is around about 3 millihertz, pretty close to where we see the frequency of this bump in the coronal power spectrum. We haven't quite sort of finalized the connection between this mechanism and what we see in the observations, but it's currently the sort of ongoing topic of my Future Leader Fellowship. So maybe next time I speak to you, I'll be able to tell you a bit more about this process. The other exciting results that I've been involved with that has come from COMP is we've actually been able to measure the coronal magnetic field, exploiting these waves. So the first bit of the puzzle that we need is to be able to measure the density in the corona. And it turns out these two infrared emission lines that are observed by COMP, the relative level populations of these two emission lines is sensitive to the local electron density. So actually, if we measure these two infrared lines, we can get an estimate of the coronal electron density. So for any COMP pairs of observations of these two infrared lines, we can use this to estimate the electron density at the limb of the corona. We can then combine this with the measurements of the wave speed. So these Alphen waves or Alphanic waves that we see. And it turns out that the expression for the propagation speed for these waves just depends upon the local magnetic field and the local density in the atmosphere. So we can measure the speed from COMP, we can measure the electron density from COMP, and this means we can then provide the first global map of magnetic field strength throughout the sun's corona. So this was a real exciting result that we managed to do this. And we showed really that the coronal magnetic field is weak, so much less than 10 Gauss in many situations, and supports, I guess, the failure of spectroscopic or spectropolarimetric measurements to be able to measure this just because it's so weak. And the future for this is that we want to take it forward and provide regular coronal magnetic field maps, as we think it may be very useful for understanding, the heating processes in the sun, and also some way providing measurements for being able to predict space weather drivers such as prominences and flares. I feel like I'm running out of time. I guess I've been almost doing 25 minutes. I can't see Emma's video. I don't know if it's popped up. She's popped up or not. So I'm just going to skip this last slide and come to my final one. So the future of infrared observations. So COMP has been decommissioned, unfortunately, and they're currently updating a new instrument to go on the SPAR at Mauna Loa, but I'm not going to talk about that one. But we've got two exciting observatories. The first is the Dki Solar Telescope. So I guess you've all heard of this. It's the solar physics latest toy, shall we say, and it's the biggest solar telescope to date. It's a 4-meter class telescope based again in Hawaii. And eventually it will have two instruments that will be able to measure infrared emission with the very catchy names of DL-NIRSP and cryo-NIRSP, where the NIRSP stands for Near Infrared Spectropolarimeter. The difference with COMP is that these instruments will only be able to measure small regions of the sun's corona, but it will be able to do it at a much higher spatial resolution. So be able to have a very focused view on these Alphanic waves and probably be able to provide very localized estimates of magnetic field through this, but with much more detail than, say, we could with COMP. The future for coronographic observations is a facility called COSMO, so the Coronal Solar Magnetism Observatory. And this is being led by the High Altitude Observatory, so the same people who design and operate COMP. COSMO is far away, though. It's kind of a future project. It's currently only in the design phase. They're still looking for sites, still planning the facilities, which is why there's only this kind of cartoonish sketch of the facility. But what they want to do is rapidly increase the size of vastly increase the size of the telescope that they were using. So the COMP instrument only has a 20 centimeter telescope of aperture. So not very big, really. And the plan for COSMO is to have something much larger, sort of a 1.5 meter coronagraph that will view much further out into the corona as well. So hopefully we'll be able to look at magnetic field strengths and wave propagation much further out in the sun's atmosphere and tying that into the solar wind as well. So I think the future is looking bright for infrared observations, if you excuse the pun, and I'll leave it there and happy to answer any questions. Thank you.
Thank you so much, Richard. That was a really fascinating talk. And I can see there are a number of questions coming through. So I'm going to hand straight to Sue so we can get through a few of those questions now. Thank you.
Thanks, Emma. I have a question from Jeffrey Greenspan. He says, although emanating from the very hot corona, solar prominences maintain a cooler temperature similar to that of the sun's surface. How? Are the prominences somehow shielded by the magnetic fields around them?
I'm not sure if they're shielded by the magnetic field. I think what happens for prominences is that they have a lot of cool chromospheric material on them. So the material, what happens when you have a heating event is it sends energy down from, say, the coronal part to the chromosphere, where you get evaporation of this chromospheric material. And along coronal loops, it's a very simple magnetic field, and that material just drains back off again. But along the prominences, the field is twisted and there are lots of dips, and the cool chromospheric material or the material that's heated ends up sitting in these dips and then cools down via radiation. And so you end up with this cool material kind of hanging in the corona just because it's stuck in dips of magnetic field. I'm pretty sure that's the general picture behind these prominences. So I don't think it's the fact they're shielded, it's just sort of denser, cool material is kind of hanging above the atmosphere.
Thank you. I have a question. You mentioned that you want to combine what you're finding out about the sun up close with its effects at Earth. What do you need to do that? What sort of data does that involve?
So, well, I'm not so interested in the effects of Earth. I'm a corona boy, really. But the aspects of the work that I'm interested in terms of the drivers of space weather is really looking at the coronal magnetic field. So the coronal magnetic field plays a role in, say, strapping these prominences down. You have overlying field above it. And once that field destabilizes in some way, then the prominence is free to erupt. So I'm more interested in trying to look at the magnetic field conditions, above prominences, and seeing if we can use that as some indicator of when the prominence might erupt. If the field strength starts to decrease for some reason, and the prominence can push up against it and escape somehow. But yeah, providing regular magnetic field measurements in the corona is kind of a key aim, and then hopefully tying that into some of these sort of predictive models that people are also creating.
Thank you. And that's about all we've got time for, I'm afraid, apart from one wonderful comment from Fabio F., who wanted to share some information about the Skylab images. He says they were actually obtained on film with astronauts retrieving exposed film canisters by spacewalking. And then they had to be individually scanned and analysed back on Earth. So probably not surprising they're a bit jerky. So thank you.
Yeah.
That's great. Thanks for reading that out, Sue. And thanks again, Richard, for a fantastic presentation. Really enjoyed that very much. Okay, so we're going to move on to our next speaker this afternoon, who's going to be Dr. Matt Nicol from the University of Birmingham, who is the recipient of the Fowler Award for 2022, and also is a recent holder of an RAS fellowship. So Dr. Matt Nicol is a lecturer at the University of Birmingham, and he obtained his PhD in 2015 from Queen's University Belfast, and was then a postdoctoral fellow at the Harvard Smithsonian Centre for Astrophysics, and also a Royal Astronomical Society Research Fellow at the University of Edinburgh. He leads the ERC-funded CRANK project, which aims to understand extreme astronomical explosions with next-generation telescopes, and holds a Turing Fellowship to apply data science techniques to improve the efficiency of detecting these rare events. So it's my great pleasure to introduce Dr. Matt Nicol now to give his presentation entitled Tidal Disruptions of Stars by Supermassive Black Holes. So over to you, Matt, to share your screen. Thank you.
Thank you very much, Emma. You see that okay?
Perfect, thank you.
Brilliant, thanks. And thank you to the RAS, of course, for having me here today. Because of the pandemic, I didn't really get the chance to do too much talking during my RAS fellowship, so this is probably a little bit overdue. So today I'm going to talk about the tidal disruptions of stars by supermassive black holes, but I want to first ground this in kind of the exciting new field of time domain astronomy. So we're very lucky right now to be around at a time where we've suddenly got all these fantastic robotic telescopes with really big CCD cameras and really wide fields of view. So these are telescopes like Pan-STARRS and Atlas telescopes in Hawaii, and Zwicky Transient Facility in California, and others. And this picture here at the top right shows the CCDs of some of these cameras compared to, here's the full moon, I think this is Andromeda. So you see how much of the sky that these new surveys can see in one shot. And because they're robotic, they can survey the whole sky with these big cameras over the course of 1 or 2 nights. And what they do then is to automatically look for any changes in brightness of any object in the field of view. So this means that we can suddenly find something like 10,000 supernovae and other explosive transients per year. What's even more exciting is that in a couple of years' time, we're going to have the Vera Rubin Observatory with its LSST survey, with it not just a huge CCD, but also it's going to be an 8-meter telescope that sees really far into the universe. And with that survey volume, we're soon going to be finding something like 1 million transients and supernovae per year. So really incredible numbers here. So what do these surveys actually see? What we astronomers get data-wise is something that looks like this plot on the left. Basically something that gets brighter and then fades away. So these data points show 2 different filters. This is a red filter and a green filter. But you see something that rises and fades away, usually on a time scale of weeks or months. We'll see the galaxy where it occurred, and we can try and classify these events with spectroscopy or in terms of their brightness and duration. So this plot shows all the different kinds of transients that we find, with the x-axis here is how long they stay bright for, and the y-axis is how bright they get at their peak. And nearly everything on here is a supernova. Mostly a type 1a supernovae, which is very useful for measuring the expansion rate of the universe. A lot of type 2 supernovae from the core collapses of massive stars. But there's a few rarer things on this diagram as well. So the thing we're interested in today are these points. You can't really see them amongst the supernovae, but we separate them out here so you can see how few there are. These are the tidal disruption events. So tidal disruption event sounds like a bit of a complicated name, but it's really a simple concept. It's just what happens to a star when it passes too close to a supermassive black hole. So this was predicted quite some time ago. This is a famous diagram from Martin Rees in the 80s that shows the path of a star here as it approaches the black hole. So if you're on this very unfortunate orbit that brings you close to what's called the tidal radius, the surface of this star experiences a stronger gravitational pull from the black hole than it does from its own internal gravitational binding energy. And what that means is that the star gets stretched out into a very thin filament. You can see here in some nice simulations. The closer it gets to the black hole, the more stretched out it gets. And if it's close enough, the star gets essentially ripped in half, and about half the material escapes off into space at high velocity, and the other half remains bound to the black hole. So this bound debris it'll begin to orbit the black hole. It'll wrap around and collide with itself. And when that happens, these streams start to emit energy. And this is what produces the flare that we can observe as a tidal disruption event. The other interesting fact about these is that the tidal radius is only outside the black hole's event horizon if the black hole is smaller than around 10 to the 8 solar masses. So in the really massive supermassive black holes at the centers of large galaxies, it's impossible to get a TDE. The star just gets swallowed whole. So this is a really effective way of picking out sort of unusually low mass supermassive black holes that are otherwise hard to see. So let's see the artist's impression. It's a bit more fun than the picture from the 80s. So here we are sitting in some swirling material. It's orbiting around this supermassive black hole in the center of some galaxy. And as the camera passes, we'll see our unlucky star. It's coming in on its approach. So as this star gets closer and closer to the black hole, it's going to experience a stronger and stronger tidal gravity from the black hole. And that's going to stretch the star out. So you can see the star starts to elongate the closer it gets to the black hole. And when it gets really close, the black hole's gravity completely overwhelms the star, and we get ripped apart into these thin streams. And you can see how some of these streams are escaping out into the distant space, and some of them are wrapping back around. And as they return to the pericenter of the orbit, that's where the energy gets dissipated. So this can be a very messy process. You can see material flying in all kinds of directions. You can see material piling up around the black hole. This could form an accretion disk, similar to what you see in other accreting black hole systems. It could drive a jet. As you can see here, we see jets from other accreting black hole systems too. I don't know why there's a shooting star, but that's the broad picture to have in mind as we go through this of what a TD might look like if we were up close. Not that you'd want to be particularly close to one of these kinds of events. So why are we interested in studying these things? So I mentioned that they're a good way to select for low mass or even intermediate mass black holes. We can also see the physics of what happens when material falls into these extreme gravitational potentials on relatively short time scales. We see these things happen over weeks or months, which is quite conducive to our observations. They let us find the central black hole populations in galaxies that otherwise the black hole would just be black and we wouldn't see it. They can potentially pick out binary supermassive black holes in some galaxies, because those would imprint on the TDE observables. And of course, these are really strong gravitational environments, so it's a perfect test bed of general relativity. The other very cool thing about tidal disruption events is that they're also what we now call multi-messenger sources. This is quite a new field of astronomy where, in addition to using electromagnetic radiation, we also try to study these events from high energy particles. So there's been a neutrino detected that was emitted by a TDE that we observed in all other wavelengths from X-ray to radio. And also TDEs should produce gravitational waves because you've got this very strong gravitational environment. So it's possible that in the next decade or so, with new gravitational wave detectors, we'll also be able to detect these things gravitationally as well as in terms of their light and particles. So this is a relatively young field, but I'm going to summarize what we know so far. So there's been a few tens of TDEs discovered over the last decade or two. Initially, they were found mostly in X-ray surveys, but since we've got all these robotic wide field optical surveys, those have been the real engines for finding more and more tidal disruption events. And it turns out they're quite a diverse population. So their peak luminosity spans a few orders of magnitude. They're all very luminous, but they vary quite a lot. Their temperatures tend to be relatively high. So the observed emission corresponds to a temperature of around a few times 10,000 Kelvin, and it doesn't seem to change. So whereas a supernova would cool down while it expands, the TDEs seem remarkably stable in their temperature, you can see here. And these last for a few weeks or months. Also observed these things spectroscopically, and that's going to be a bit of a focus today. So spectra of TDEs are also quite diverse. One thing they have in common is broad emission lines. So the width of these lines are something like 1,000 or a few thousand kilometers per second. And they show quite complex profiles. So they have been difficult to interpret in terms of is it scattering or expansion or rotation or something else that's broadening these lines. There's at least 3 different kinds. So some TDEs show only emission from hydrogen, the Balmer lines H alpha and H beta. These are the yellow objects at the top here. Others show only ionized helium emission, which is this blue line down here. And then other TDEs show a mixture of hydrogen and helium, and also sometimes with this nitrogen 3 line here, which also turns out to be quite important. So there's a lot of disorder in this class, and we want to try and impose some order and understand what's really going on here. So I want to focus on one particular question that's been, I think, one of the main focuses of TDE research over the last sort of 5 or 10 years, and that's what's been dubbed the cool photosphere problem. So the problem is quite simple. Basically, this says that if the emission we see from tidal disruption events comes from an accretion disk of material orbiting close to the black hole, the temperature should be something like 1,000,000 Kelvin, which is about 100 times higher than the temperature we actually observe. So the TDEs we see are hot, but they're not that hot. So the lower temperature suggests the radiation must be coming from further out than a typical accretion disk. So what we call a cool photosphere at larger radius. But we don't know how this happens. The TDEs also show a very wide range of optical to X-ray ratios, with some showing X-ray luminosity comparable to the optical luminosity, which you probably would get from an accretion disk, and some showing essentially no detectable X-rays down to very deep limits. So a related question to this is why do only some TDEs show X-ray emission? So for the past few years, we've been trying to tackle this using spectroscopy, essentially, with a range of telescopes. So the ones shown here are the Magellan telescopes, the ESO Very Large telescopes, and a particular favorite of mine, the NTT New Technology Telescope via the PESTO Transient Survey. These are all in Chile. The telescope's pictured here. We've been using these to get lots of nice data on TDEs. So I'm going to start with the question of where does the optical emission come from? And we're going to look at this via a case study of a particularly X-ray faint TDE, so one that we saw bright optical light but no X-ray light. This object was called AT 2017 EQX because it was discovered in 2017. This was found by the ATLAS and the PAN-STARRS surveys. And what you see here is the light curve detected during the rising phase here. And then when we realized it was a TDE, we triggered all this extra ultraviolet and optical photometry. And we also have a nice series of spectra here to show how it evolved as well. So if we look at the spectra in a bit more detail, I've subtracted off the continuum here to highlight the lines. You can see two main features. So this big broad feature here is the helium-2 line, and this broad feature is the hydrogen alpha line. And as the spectra evolve, the helium line doesn't change too much in flux, so it does develop a bit of a blue shift, whereas the hydrogen line completely disappears by something like 3 or 4 months after the disruption. In terms of the luminosity ratio, it goes from about a helium to hydrogen ratio of around 2 to helium to hydrogen ratio of bigger than 10. We can't measure it because the hydrogen's gone. So this is a really surprising evolution at the time. So we were actually had to go back into the theoretical literature to try and figure out why this happened. So it was a really nice paper just the year before this TDE that was trying to determine what sets the line ratios in TDEs. And this adopted a model where every TDE is surrounded by some kind of extended atmosphere, and the different emission lines from different elements are produced at different heights within that atmosphere. So that's what the schematic shows here. So the continuum luminosity, and the bulk of the emission comes from deep inside here, but the H alpha emission comes from very close to the surface, while the helium emission comes from somewhere in between. What that means is the more compact the atmosphere, the less volume you have over which you can emit the H alpha photons. If you go make the atmosphere too small, all the hydrogen gets self-absorbed. So that produces model spectra that looks something like this, where the red is the smallest atmosphere, the blue is the largest atmosphere. And you can see below a certain scale here, the H alpha line disappears, while the helium line still remains quite strong. So how does that relate to our particular TDE? So this plot now shows the luminosity evolution over these few months that we were able to observe it, the temperature evolution, and the evolution of the effective black body radius. And what we see is that at early times around the peak of the light curve, the effective radius was something like 10 to the 15 centimeters. And by 100 days later, it had decreased to around 10 to the 14 centimeters. And that's kind of the scale that these models were produced to study, which is quite convenient. And in fact, at early times, the predicted flux ratio of H alpha, or helium-2 over H alpha, is around 2, which is exactly what we saw in our observed spectra. And over here, the predicted ratio is that the H alpha has just disappeared, which is also what we saw by about 100 days. So this model that was produced the year before the TDE seems to perfectly explain the line evolution we saw once we fold in the fact that the radius is changing. And this has since been confirmed for a large number of TDEs. So my collaborator, panelist Charles Popoulos, produced this lovely plot that shows lots of different TDEs with the radius at different times during their evolution versus the corresponding helium-2 to H alpha ratio. And there's a very clear trend in this plot that shows essentially the larger the radius, the lower the ratio, i.e. the more hydrogen emission we can see in the spectrum. So this is very strong evidence that the optical luminosity in all of these TDEs is coming from a similar extended atmosphere that produces the cool photosphere somewhere further out, and then this extent of the atmosphere determines which lines you actually see in the spectrum. So I think the answer to part one is that we must have an extended atmosphere around these TDEs, and that's where our cool photosphere lives. But if we've got an atmosphere, where does it come from? Is this some pre-existing debris? Does it come from the TDE itself? Is it the bound or the unbound material? There's a lot more questions that this raises. So I want to move on to another case study, and I want to show my favorite TDE. This is called AT 2019 QIZ. I've called this the Rosetta Stone of TDEs, and that's because the data we obtained for this one was so nice because it was so nearby, but it's the closest TDE to date, that we've been able to really break a lot of degeneracies in our understanding of these objects using this one. So it's only 65 megaparsecs away, and it's in this beautiful barred spiral galaxy. And it was detected by many surveys, including the Gaia satellite. And because Gaia has this incredible astrometric precision, it was able to say that this source was exactly in the center of the galaxy to within 12 plus or minus 30 parsecs, which is fantastic. So here's the light curve of this TDE. And you can see the big difference between this one and a typical TDE is that because it was nearby, we identified what it was early. And so we triggered all the extra photometry with our UV and infrared telescopes much earlier in the evolution compared to what we usually have. So we've actually got the multicolor information before the peak of the light curve. We also detected this one in the X-rays and the radio, so we have a full spectrum of information to analyze this event. So using all this color information, we're able to measure the total luminosity and the radius of the emitting region from very soon after the disruption. So this plot shows the luminosity evolution in black and the radial evolution in gray for the first 30 days after the disruption. And what we see is that the radius increases incredibly linearly, corresponding to a velocity of about 2,000 kilometers per second. And the luminosity increases very close to time squared, which is exactly what you'd expect for a constant temperature, constant velocity outflow. Interestingly, the only other two TDEs with early data also show a rise proportional to time squared. So this is probably a phenomenon that's applicable to a lot more TDEs. We also got an amazing series of spectra for this event. You can see the evolution here from well before the peak to 6 months later. And it evolves from this very blue, very hot continuum with extremely broad emission lines to a galaxy-dominated spectrum with still significant emission from the TDE, especially this H-alpha line here, but much narrower by that time. I want to highlight just a few of the best spectra. So these are all obtained with the ESO Very Large Telescope, 8-meter telescope in Chile. And this is a spectrum roughly at the peak of the light curve, 1 month later, 2 months, 3 months, and 4 months after the disruption. So this is a zoom in around the helium-2 part of the spectrum. So what we see here is initially the helium-2 line is significantly broadened and blue shifted compared to its rest wavelength here. By about a month later, this blue shift has gone away, and we have a helium-2 centered exactly where it should be. By another month later, the helium-2 has essentially disappeared, and what we see instead is this nitrogen-3 line. And after that, we just see the nitrogen-3 getting stronger and stronger. So this actually tells us a lot of information about what's happening in this tidal disruption event. Especially the nitrogen-3 line is actually a way to see a hidden UV continuum. So we have no telescopes that can see extreme UV emission. And in the case of the TDEs, it could well be concealed behind this atmosphere anyway. But if you have a nitrogen-3 line, it tells you that there's a fluorescence process going on called Bowen fluorescence. And this is a process where you have very high energy photons that ionize some helium-2. And when the helium-2 recombines, it emits some photons that triggers a cascade that excites oxygen and nitrogen until we see these other lines in the optical. So if we see nitrogen-3, that means we know that there's a hard ionizing continuum of extreme UV and X-ray photons. So that's very useful information. The other interesting thing about the spectra is if I focus on the first one, the one before the peak of the light curve, with the very strong blue shifts, and I compare this to some theoretical models. So in fact, the shape of these lines exactly matches some models of very dense electron scattering outflows with velocities of around 5,000 to 10,000 kilometers per second. So as well as our initial radial expansion that we saw in the black body fits, we now have evidence from the spectra showing there's an outflow. And we also have evidence from the radio. The radio data can be modeled with a velocity of around 10,000 kilometers per second expansion as well. So you've got all kinds of evidence pointing to rapid expansion in the early phases of this event. So if we're convinced that this thing is driving outflow from soon after the disruption, what would actually power that? I think the clue here is in the nitrogen-3 lines, as well as the X-ray detections of this event. So you can see here in the bottom plot, this is the X-ray light curve. And over the first 30 days or so, you've got this rising X-ray emission. So both the nitrogen-3 lines and the X-rays point to accretion onto the supermassive black hole. So there's energy released by material that's really falling onto the black hole. If the accretion rate is very high, which is what you expect at early times from TDE simulations, this material doesn't have time to radiate. So it gets very, very hot. And this pressure basically drives out basically a very extreme stellar wind equivalent that causes this gas to expand at high velocities. So with this, we can put together, I think, a complete picture of the evolution of this event. This is probably the most complicated slide, so do bear with me. But what this shows is the luminosity evolution in the optical and the X-rays, the temperature evolution, and the evolution of the emitting radius. And what we see here is initially, we have energy being input from accretion, as evidenced by the rising X-ray light curve, which goes into both heating up the debris and making it glow, but also into causing it to expand. During the early phases of expansion, this material is very, very dense. And that's why we have these blue shifted electron scattering line profiles, and also a constant temperature plateau. The material can't cool because it's too dense. And during this phase, we see the very linear increase in the radius. Eventually, though, we get to a point where the material is expanded enough that it can cool down because the density has decreased. And at that point, we see a stall in the photosphere and a really, really rapid decrease in the temperature. So this is where all those trapped photons start to escape. After that point, then, the density just continues to decrease as the outflow gets bigger and bigger and bigger. And so as the density goes down, we see further and further inside it. And the further inside the outflow we can see, the more X-rays we see. This X-ray to optical ratio keeps increasing. And the lines change from helium-2 to this nitrogen-3, which is the other signature of accretion. So basically, we're seeing more and more of the actual inner engine driving the accretion flow as the outflow expands and cools. Or to put it very succinctly, we change from an outflow-dominated spectrum to an accretion-dominated spectrum. Over the few months, we're able to observe this event. So I think that this lovely nearby TDE gives us really strong evidence that this atmosphere that reprocesses the X-rays is actually launched by the TDE itself, and it's probably powered by accretion onto the black hole. So the final question I want to ask today is if we have accretion buried inside this atmosphere, how does this accretion process actually operate? So in most accreting black hole systems, like an active galactic nucleus or an X-ray binary, this accretion is mediated through a disk around the black hole. Is this the case in TDEs as well? So I'd say that on long time scales, the answer is certainly yes. So this plot shows 4 quite old TDEs that we've been able to observe for 10 years or so. And what you see here is the initial flare at early times, and then for thousands of days later, so 10 years or so, the luminosity stays remarkably constant. So you've got this completely flat luminosity evolution. And the explanation for this is that the TDE is sort of quieted down and settled down, and what's left behind is a stable disk that you can see in the ultraviolet. So we know TDEs make disks eventually. The question is, when did the disk actually form? Well, simulations predict that the disk can actually form within a single orbit of this bound debris. So this shows simulation over one orbit from Bonner and Liu, and you've got this nice circular accretion disk by the time that this is finished. I think for the first time a couple of years ago, we actually saw the early time disk again in the spectrum of a nice nearby TDE. So this is a work led by Phil Short, who's a PhD student at the University of Edinburgh. And this TDE shows initially at the peak of the light curve a clear outflow profile similar to 2019 QIZ. But within the first month of its evolution, you've got this flat topped and then double peaked H alpha emission line profile. So Phil called this El Diablo because of the 2 horns here. But what it's telling us is that you've really got inclined circular accretion disk that you can fit really nicely with this model from the 80s that shows the 2 peaks in the H alpha from the approaching and the receding side of the rotating disk. So we know from this event that at least some TDEs do form accretion disks really early in their evolution. So why do we only see it sometimes? So try to piece all this together, what I've shown you today. This has been dubbed the unified model of TDEs, where we think that a typical TDE consists of a compact accretion disk surrounding a black hole that drives a fast outflow above and below the plane of the disk, and potentially slower outflows closer to the edge of the disk. And what we see depends on our viewing angle towards the system. So if we see a TDE from the side, we're mostly seeing atmosphere. We might get a line evolution like 2017 EQX. If we look from sort of intermediate angles, we'll see the fast outflow. And if we look from close to the pole, we can see all the way down to the disk, and we might get line profiles similar to 2018 HYZ. So this model is fantastic because it makes a clear prediction. And that's that if we see bright X-rays, we should also see fast expansion velocities, because both of these things come from close to the pole. So the next step, I think, is to test this with large samples of TDEs. And that's what we're aiming to do in the future. So I'll just skip over these couple of slides to bring it to the conclusion, because I see Emma's turned her camera on. So to get these large samples of TDEs, I mentioned at the start, the Rubin Observatory is going to be the ultimate discovery machine for explosive transients. It's been predicted that Rubin should find 10,000 TDEs over its 10-year lifetime, and that compares to the sort of 50 TDEs we know so far. So this is going to be an incredible opportunity to learn more about these events and to measure the masses of thousands of supermassive black holes in all kinds of galaxies. So I'll leave this nice picture of Rubin and I'll conclude there.
Thank you so much, Matt. That was a fascinating talk, and I've personally learned a lot. So thank you very much for that presentation. I'm going to hand over to Sue to see what questions we have coming in.
Thanks, Emma. I have a question from Jeff Greenspan. It's sort of two questions, but now that you've got these bigger populations, can you distinguish between different types of stars, main sequence stars, later stage stars, and gas clouds? And does the nature of the supermassive black hole, perhaps its spin state, have any effect on what you see?
That is a fantastic question. In fact, that's some of the slides I skipped over there were kind of to do with that. So let's see if I can. I can't make my slide go back. If I go to here, so we can actually measure a lot of properties about the orbits and the stars from fitting models to the light curves. So this shows the 3 TDs I talked about with physical models fit to the light curve. You can see we get really nice fits in all the different bands here. It looks like from the free parameters of this model are things like the mass of the black hole, the mass of the star, how close the star passes to the black hole. It looks like there are differences between the different spectral types in the distributions of these parameters. So for example, the ones that show only hydrogen seem to come from slightly lower mass black holes, and they don't pass as close to the black hole as do the ones that show helium lines. So it could be like this, where different kinds of TDEs come from different kinds of orbits around different masses of black holes. If you've got a very big black hole and a very close approach, the stream wraps around much tighter and forms a disk much more quickly. Whereas if you've got a low mass black hole or sort of grazing encounter, the streams intersect far away from the black hole, and that might make a much larger atmosphere where you see more of this hydrogen emission. In terms of the masses of the stars themselves, it looks like the population is mostly consistent with low mass main sequence stars, but there's a slight selection effect where the smaller the star, the bigger the mass range of black holes that can disrupt it. So it's so we're always going to be biased towards finding quite low mass stars with TDEs.
Okay, thank you. I believe we have a question from our chairman.
Thanks, Sue. So Matt, I'm just wondering, and this may not be your sort of area of study yourself, but I'm wondering thinking back to Richard's talk, what role does the magnetic field of the star play, and how does that affect the interaction or indeed the debris that is sort of taken away from the star as it passes past the black hole?
That's a very difficult question. The old magnetic field angle always makes it really tricky, but I think from some of the simulations, this simulation here from Jane Dye, this was a magnetohydrodynamic simulation. So at least some of the wind driving from the disk is almost certainly to do with magnetically driven winds, but I wouldn't be able to tell you what's the relative importance of the thermal versus the magnetic contribution and things like that. But I think the best simulations are starting to take into account the fact that these disks, they should have magnetic fields, but I'm not sure what the overall impact is. Some TDs show very clear jetted emission in relativistic jets, and those must be magnetically collimated, I think. So those ones should have strong B fields.
Thank you.
Okay, thank you very much. And we have just time for one more question. It might have to be quick. This is from Nilesh. What's the benefit of knowing the masses of the supermassive black hole involved in these events? Might this help you plug the mass gap in low mass black holes?
Yeah, that's certainly what we're hoping. It's still not a solved problem how black holes reach the masses that they do, by early times in the universe's history. So it's quite possible that early in the universe, black holes go through a period of eating lots of stars. So if we're able to measure the masses of black holes in all kinds of galaxies, and if we're able to correlate that with the TDE rate, it might tell us a little bit about how these black holes grow. And indeed, we might be able to find some intermediate mass objects too, because those can tightly disrupt the white dwarf. And those are the ones we might see in gravitational waves in the 2030s when the LISA space detector is flying.
Okay. Thank you very much.
Thanks.
Great, thank you, Sue. And thanks again, Matt, for the fantastic talk. Okay, so we're going to move on to our third and final talk for this afternoon, which is going to be given by Professor Giovanna Tinetti from UCL. And Giovanna is the RAS Eddington Lecturer for 2022. So Professor Giovanna Tinetti is the head of astrophysics group at the University College London and also director of the UCL Centre for Space Exochemistry Data at Harwell. She's the principal investigator of Ariel, the European Space Agency's science mission to be launched in 2029. She's also co-founder of Blue Sky Space Limited, which aims at creating new opportunities for space science satellites. Awarded a PhD in theoretical physics from the University of Turin in Italy in 2003, Giovanna Tinetti has continued her academic career as NASA Astrobiology Institute Fellow at Caltech JPL, and then as European Space Agency Fellow in Paris, before moving to UCL in 2007 as STFC Aurora, and then Royal Society URF Fellow. She has authored or co-authored over 200 research papers and has delivered over 250 talks, seminars and public lectures internationally. So a very warm welcome to you, Giovanna, to give the Eddington lecture today entitled A Chemical Survey of Planets in Our Galaxy. And I'm happy to hand over to you now to share your slides. Thank you.
Good afternoon to everybody, and thank you so much, Emma, for this very nice introduction. I feel very honored to be here today to give you this talk, unfortunately online, but hopefully we will meet all at the RAS very soon. Okay, so during the past 30 years, we have learned that planets are ubiquitous in our galaxy, and we're expecting that planets are at least as abundant as stars. So unfortunately, we don't know yet all these billions of planets that we're expecting. But what we have learned is that at least 5,000 planets have been confirmed through a number of techniques and observatories from ground and from space. And the vast majority of these planets are organized in planetary systems. But what I think is the most revolutionary message that we're getting out of this observational evidence is the fact that the solar system doesn't seem to be the paradigm of planetary system in our galaxy. Exosolar planets, planets around our stars, seems to be much more diverse compared to the planets in our own solar system. And to make my point, I'm just showing here two plots where we're looking at the planetary radii of some of these planets discovered. The discovered planets are these colorful dots as a function of the distance between the star and the planet, or the orbital eccentricity. And as you can see, all exosolar planets detected so far seem to show a much higher diversity compared to the planets in the solar system, which are also indicated in this diagram. And I think the biggest question here is understanding why the solar system is not the paradigm and why we're seeing all this diversity out there. When it comes to galactic statistics in terms of planets, I think Kepler was really fundamental to understand how does it look like. And in particular, Kepler, and of course other techniques and observatories have confirmed this sort of view. But Kepler was the first one to show that small planets seems to be really the most common type of planets in the galaxy. And this was something that we were not necessarily expecting. And so in particular, it seems that planet in between the size of the Earth and the size of Neptune, a category that we're not now calling super-Earth or sub-Neptune, in part to hide a bit our ignorance, because we don't know too much about this type of planets, because we don't have any super-Earth or sub-Neptune in solar system. But it seems to be the most common out there. And most recently, some additional measurements from the ground to refine a little bit better the properties of the stars that are hosting these planets, and also using some of the Gaia measurements, have shown that these small planets are coming in this sort of bimodal distribution. We are speculating that the planets that are clustering more around the size of the Earth are possibly more rocky type, and on the contrary, the other peak in the bimodal might be suggestive of planets that are more volatile rich, so more rich of water or hydrogen, but we don't really know that so well. We believe that this diversity that we're seeing there must come from how planets are forming and evolving in our galaxy. But of course, we need to have some observational constraint. And when it comes to planet formation at the moment, most of the information comes from these really beautiful images, but also the complexity of chemistry that we're seeing in disks, in particular using ALMA or direct imaging instruments in the near infrared. So clearly, circumstellar disks are the environments where the planets are forming. And so understanding their complexity, both in structure and also chemistry, is telling us something about this environment where planets form. But also some constraints are coming out of the solar system, in particular about isotopic ratios that are measured in meteorites or in situ in some of the bodies in the solar system. And also all this information is helping to provide a clock and some constraint in the history of the solar system. But still, we still have many open questions. And in fact, we really want to understand why the solar system is as it is, why exoplanets are so diverse, what they're made of. Of course, we're interested about also the weather, their diversity already mentioned, and in particular, we want to understand if and how this diversity might be linked to how planets are forming, how they're evolving. And of course, we have a lot of interest about potentially habitable planets. So what do we know so far? Well, most of the time we know very little about these planets. For the planets which have been detected through transit, we know their size. In some cases, we know their masses out of measurement with radial velocity. And then we know basically the distance between the star and the planet, out of which we are making some speculation about the potential atmosphere of the planet. And so we estimate the planetary temperature. But as you can imagine, all these parameters are very useful, but are still very basic. And so, of course, if you know the mass and the radius of these planets, you can calculate the bulk density. And so at zero order, you can start to map some of the interior structure model that are more suggestive of some of these planets being more rocky type or more volatile rich, or on the contrary, more similar to some of the gaseous planets in our own solar system. But of course, this mapping is not very precise. There is a lot of degeneracy. And in particular, if you focus in on smaller planets, in particular the super Earths or the sub-Neptunes that I was mentioning before, there is a huge degeneracy of interpretation if you only have the bulk density. And so clearly we need to know more about these planets in order to understand their nature. One way to go is to look at the atmospheric composition of these planets. And the reason why the chemistry of this atmosphere can be very useful is because they can be really a tracer of the nature and the history of these planets. And this is because the chemistry of an atmosphere is the outcome of many complex physical and chemical processes that can happen in the atmosphere that involves basically the formation, depending where the planet is forming in the circumstellar disks, the kind of chemistry and the kind of chemical components that they kind of create at the formation can be very different. And so we are speculating that when planets are already formed, somehow they might still bring some information about the provenance in the where they form in the protoplanetary disk. But also, if we're looking at rocky type of planets, we expect that in particular in the early phase of their formation and evolution, when they cool off potentially some volcanic activity might be present. And so maybe some molecular species are outgassed in the atmosphere. And of course, well, one would expect at least that these chemical species are connected to the composition of the interior somehow. Also, there are many escape processes in the upper part of the atmosphere because, of course, there is an interaction between the radiation coming from the star and the upper part of the atmosphere. And so all these escape processes can either through time really get rid of the atmosphere in some cases, in some more extreme cases, or in any case, modifying the composition quite effectively, and so on and so forth. I don't have time to go through all this, but this is just to say that if we do have access to the atmospheric composition of these objects, then we can learn quite a lot about how they formed and how they evolved through time. And luckily, today we have already many different techniques to probe the atmospheric composition, but also the atmospheric structure of these extrasolar planets. And it's quite amazing, I would say, that you already have all these techniques, considering that this measurement typically involves extremely precise and accurate measurements, typically of a few parts per million. And so, as you can imagine, is far from being easy. But transit, direct imaging, or high dispersion from the ground are all techniques that today are extremely successful to tell us something about these atmospheres. Now, for the sake of time, I don't have really time to go through all these techniques, so I will just show you a few results so you can appreciate what has been done so far, in particular focusing on the transit method and focusing more on space observation. At the moment, we have the information about the atmosphere of about 80 Jupiter-type planets, so the bigger one, more gaseous, and typically hot objects are also easier to be probed. Although little by little, we are also able to probe colder objects, and in some cases, some of the measurements were done in a way to follow the planet all around the orbit. So basically monitoring the what we call phase curve. So where the planet is passing in front of the star, but also going behind it during the eclipse. And when we have access to this sort of observations, it's extremely valuable because you can really follow the planet around the star, and you can understand also, in particular, how the thermal structure of the atmosphere is changing, because, of course, we're looking at a different hemisphere in the planet while the planet is orbiting around the star. Many of these planets are orbiting around the star in a very short distance, and so we believe that many of these objects are tidally locked, and so the hemisphere that is irradiated well, we have one hemisphere that is always irradiated, and one hemisphere, on the contrary, is always in the darkness. But unfortunately, we don't have so many phase curves for so many objects. Even the observation and the observatories that we currently have, in particular, Hubble is still operating, and there are a few instruments that have been used actually to probe the atmosphere of exoplanets. Hubble and Spitzer, of course, they have their own limitation, but even with the current instrumentation, we're able really to push some of these measurements to look at even smaller and colder planets. And one example is this K2-18b, which is one of these small planets. Has a radius that is twice the radius, a little bit more than twice the radius of the Earth. And we still don't know too much of its nature, whether it is a so-called ocean world. So basically a world where the interior is a mixture of rocky and ices, and perhaps even an ocean at the surface, or on the contrary is more a sub-Neptune. We don't know because we still have some uncertainties, not necessarily on the radius and the mass of the planet, but more on the radius and the mass of the star. And given that, so when you're measuring the radius and the mass of the planets, are always in units of the radius and the mass of the star, clearly this uncertainties is brought forward. So we still don't know too much about the nature of these objects, but we do know that there is water vapor in the atmosphere. And so this makes this object that is relatively cold around the temperature of the Earth, really, an extremely interesting one. So these are just some examples to show you what many teams, in particular, there's an observation that was looked at, so UCL, are been doing with current instrumentation. But of course, today I want to focus a little bit more about the future, and the future is quite bright because we already have a number of dedicated observatories from space and the ground dedicated to exoplanet detection. In particular, TESS is currently operating and extremely successful. The number of exoplanets discovered by TESS is increasing by the day, and it's wonderful. And also the ESA Cheops mission is working extremely well. And of course, the launch on James Webb is extremely exciting because we're all looking forward to have a much better measurements with these incredible observatories, in particular, looking at the atmosphere of smaller and colder planets. Later into the future plateau, probably 2027 will be launched, so even more and more diverse planets to be discovered. But today I want to focus on Ariel, the Ariel space mission. And the Ariel science objectives were really put together by the Ariel team to address the kind of new question that I was mentioning before. And so in particular, we're interested at answering questions like what are exoplanets made of, what are the physical processes that are shaping the planetary atmospheres. But more in general, we really want to use the chemistry of these exotic planets to understand how planets and planetary systems form and evolve in our galaxy. And so how do we do that? How we plan to do that? So Ariel was proposed to European Space Agency in 2015, and it was selected in 2018 to be the ESA M4 mission, and it was finally adopted in November 2020. And so now we are working for having a launch in 2029. Ariel will be launching L2 at 1.5 million kilometers away from the Earth, and this will be a dual launch. It will be launched with Comet Interceptor, which is another extremely interesting mission. Ariel is a 1 meter class telescope, and the unique selling point is to be able to do measurements of exoplanet atmospheres and simultaneously covering between the visible and the infrared, in particular covering a relatively broad wavelength range between 0.5 and 7.8 micron in the infrared. And the fact that we're doing it simultaneously, it's quite an advantage because as you can imagine, many of the stars that are hosting planets are not necessarily very quiet stars. They might be active, and the activity of the star can interfere when you're pushing measurement to a level of precision of a few parts per million. Clearly, the stellar activity is a source of noise, and so you need to make sure to be able to get rid of that. And being able to cover simultaneously the visible and the infrared is a big advantage. But it's also a big advantage in terms of efficiency because you don't have to repeat measurements in order to get information over this very broad wavelength range. And because of that, because of this efficiency, we are able, during the lifetime of the mission, that is about 4 years, but can be extended to 6 or more, we will be able to observe about 1,000 exosolar planets. And we really want to make sure to cover a broad parameter space in terms of planetary size, but also type of stars, temperature of planets, and so on and so forth. And so we want to include both rocket type, a more gaseous one, and temperature that goes from relatively temperate to extremely hot, and really stars that go from A star, so a large one, down to a dwarf. The Aerial Payload Consortium is growing, in particular after the adoption. Many more scientists and engineers have decided to join the team. So we have now 500 scientists and engineers from 16 ESA countries. And we have the participation from NASA and JAXA. So it's clearly a large team. The picture that you're seeing here, it dates back to 2020, was the last meeting that we did in ESTEC just before lockdown. And so we're looking forward to the possibility to do another consortium meeting in person, because it wasn't really completely possible so far. The aerial instruments will be assembled in Didcot. You can see here a picture of the clean chamber at RAL Space, where will be assembled. And just a few months ago, there was the announcement that the prime has been selected, and the prime is Airbus. So Airbus will build the aerial spacecraft. So why we selected this wavelength range between 0.5 micron in the visible down to 7.8 micron in the infrared? Well, we have done a lot of work actually, even before proposing aerial to the European Space Agency. And the reason why we're selecting this wavelength range is because we want to be able, in particular, shorter wavelength. I already mentioned the fact that if you want to look at the activity of the star, you can see the activity mainly in the optical, and so being able to probe at least a 0.5 micron is very valuable then to correct the activity along the wavelengths. But also, if you have clouds or hazes in these hemispheres, you see in particular if clouds or hazes are made of relatively small particles, you're able to see them and characterize them mainly in the optical. On the contrary, you really want to be in the infrared if you want to extract information about what kind of molecules are present. And you see here a long list of molecules and their unique signatures in the infrared. But also if you want to probe the temperature and the thermal structure of this atmosphere. So it's really an unoptimized choice. In the consortium, we have more than 20 science working groups that are working on different science topics and aspects. So there is a lot of work that has been done and is still being done. But also on the ESA side, an area science team has been appointed. And the reason why I'm putting this list up here is because I'm very pleased that we are 4 people from the UK. Myself, Olia Panic from the University of Leeds, Sarah Caswell from the University of Leicester, and then Paul Ecclestone of RAL Space. He's the project manager for area. The kind of observational strategy that we have considered is a sort of 40-year approach, because with this mission, we want to be able to study both individual planets and really extract the nitty-gritty detail of some of these hemispheres, but we also want to do a population analysis because we want to extract also some statistical properties for which you really need to have a large sample. And so we have this sort of wedding cake sort of structure where we want to go for a survey first for 1,000 planets and select progressively a smaller number and really go deeper in order to extract more information for the most interesting objects and also consider to repeat many observations on a more limited number of objects to look at atmospheric circulation. And also we're expecting a lot of variability in these hemispheres, but we don't know necessarily the sort of spatial and temporal pattern for this variability. So the way to go is really to keep observing a few objects over and over through time. We already have a plan for the mission for the 4-year and also for the 6-year. And so we already have a list of targets. Most of the targets that we have so far were detected out of tests, but also from the ground. But of course, this list and this program is evolving because the number of exosolar planets and interest in exosolar planets that are being discovered is changing by the day. And so between now and 2029, we are really prepared to evolve this plan. But already right now is quite fantastic. And the kind of parameter space that we're able to probe with known planet in terms of size, temperature, type of stars, and so on and so forth is already really, really very diverse and interesting. And of course, we want to focus also on planetary systems, not necessarily only on single planets around stars. And in particular, TESS has discovered many planetary systems, and we're very curious to look into those, because if you're seeing some chemical diversity in the same system, then this diversity might tell us something about how these planets have formed and if and why they are diverse. I don't want to spend too much time in describing the detailed program that we plan to do, but of course I'm more than happy to answer a question after. But just a couple of slides to give you an idea of some of these science questions that we want to address. Small planets, as I mentioned before, are very interesting and a little bit of a mystery, because these objects in between the size of the Earth and the size of Neptune, they don't really exist in the solar system. So what are they? And so, as you can imagine, there is a lot of theoretical work in trying to understand the potential interior composition, and going from more silicate type of planets, like the planets like the rocky planets in our own solar system, but also more exotic ones. So for instance, from a theoretical perspective, one could imagine even planets that are more carbon rich, with an interior that, instead of being made of silicate, is more made of silicon carbide. Or one could think that many of these objects that have a density that is lower than the silicate planet, they might contain some volatile in the interior, and so maybe some layers of ices or even water mixed with some rocks. So of course, as you can imagine, the number of possibilities is really huge. And if you just have one number, the density, it's very hard to understand what's going on. But if we have on top of it the composition of the atmosphere, then we can start to understand whether or not this composition might tell us something about the interior. In particular, if we're looking still at relatively hot objects, one could imagine that for hot objects, the atmosphere is a better window for what is happening in the interior. And so this might be really very interesting planets to look at. But I also mentioned before the interest that the entire community really has in planet formation, because if we don't understand how planets are forming, then we probably don't understand the diversity that we're seeing out there. And in the literature, there is a lot of interest in trying to correlate the elemental ratios. And so, for instance, ratios between carbon and nitrogen, or carbon and oxygen, that can be measured out of the molecular composition of this atmosphere, and one can try to correlate these elemental ratios with the provenance, in particular of the giant planet, the provenance in the protoplanetary disks. And so the plot on the left is showing some simulations, but what is interesting is that the kind of precision and accuracy that aerial spectra will deliver will be able really to give this elemental ratio with high level of accuracy. And so we'll be able to make these measurements for a large number of planets and understand whether or not it's true that there is this correlation between formation and elemental ratios. I also want to spend just a few minutes to talk about the challenges, which has been an initiative that at the beginning I started, I don't want to say more for fun, but we wanted to engage with the open community working on machine learning globally, and try to understand whether the kind of techniques that we have been planning on using to analyze many of the aerial data are the best one, or on the contrary, in the global community of amateur and professional working on machine learning, we could learn something. And so that's how the entire DOA Aerial Data Challenge have started. But we're seeing a huge potential out of these aerial data challenges. And the one in 2019 and the one in 2021 were a huge success. We have received the participation of over 100 international teams. They were organized in collaboration with European Conference on Machine Learning. And in these two cases, the challenge was about extracting aerial extracting chemical informations out of simulated data that were very noisy, with a lot of systematics and potential also stellar activity. Now, the good news is that the results from this two aerial data challenge were extremely useful, and all the techniques that have been proposed by some of the winning team are really very helpful, because they independently are suggesting that we can get to the kind of precision that we want to reach, in this particular case, 10 parts per million. So with this kind of precision, we are confident that we can extract the molecular composition and atmospheric structure as we were planning. A funny note, the Aerial Data Challenge in 2021 was awarded to a small company in Portugal, and Luís Simões was the winner. And he has become quite famous in Portugal. And as you can see here, it was, well, there was a question about the Aerial Data Challenge in a TV quiz in Portugal. And so it really shows that some of these initiatives can really have a very nice visibility and exposure, and the public also can engage with what's happening. We're already preparing the Aerial Data Challenge in 2022, and this time we will have the contribution and collaboration with Dirac and the Alan Turing Institute, so we are planning to go even bigger. And as I mentioned before, they started a little bit more, I don't want to say as a game, but certainly as an engagement activity. But actually, we have seen that we're learning enormously out of this collaboration with the global community. And so clearly the intention is keep doing that. Because we really want to make sure that we're learning the best AI techniques to analyze the data. Just a few words to say that James Webb and Ariel are highly complementary. Ideally, if James Webb can live for 10 years, they might be even well, we might even be able to do some simultaneous observations with James Webb and Ariel. But more in general, of course, we have compared the performances of James Webb, Ariel, and of course, Hubble. And what we are seeing is that Ariel has similar performances to James Webb if we're focusing on warm and hot planets around bright stars. And so it really shows the potential of Ariel. Whereas, of course, with James Webb, you really need to have James Webb if you want to focus more on small planets, in particular cold one. And so there is possibilities of synergies, but also complementarities. And we really want to make sure that the measurements out of James Webb will be used really to plan and to refresh what is the strategy for Ariel. There is also highly complementarity between aerial observations and the ground-based facilities from the ground. What you can do from space is to cover a relatively broad range, because being in space, you don't have the telluric contamination of the Earth atmosphere. And so you can really probe a large wavelength range. But of course, these are at the expense of having a smaller telescope. And so you need to compromise with the kind of spectral resolution you can achieve. On the contrary, from the ground, if you look at the simulated performances from the ELT, then you can get incredible spectral resolution, which is fantastic, in particular if you want to focus more on atomic lines or single lines, or even potentially some isotopes. But that can be reached typically in a relatively narrow Wellian range, and so you can't necessarily see the continuum. And so again, if you're able to use aerial and measurements from the ground from large facilities together in synergies, then it's fantastic what you can reach. Couple of words about a citizen science program that has been extremely successful, called ExoClock. That started it's an open platform, and it started to monitor the ephemerides of targets that are good for aerial, with the contribution of the public, and in particular amateur astronomers. And again, it started with a very small team, with a sort of niche initiative, but actually is having an incredible success, and many papers are already being published. The last one was in APJS, monitoring the ephemerides for hundreds of planets. And currently ExoClock, that is being coordinated by Anglos Tiaras, is seeing the participation of 480 participants. 77% are amateurs from many countries around the world. So it really shows the impact that you can have when you work together. And so it's really fantastic to see the results. So if anybody online is interested in participating to this initiative, you can just look at the website of ExoClock, and you can look at the priorities of targets that for which we still need to have monitoring on the ephemerides. You can join the team. Before I close, I just wanted to say that the Aerial Consortium wants to take a very open approach when it comes to data. We think it's very, very important the data are out as soon as possible. And so in the Science Management Plan that was approved at the aerial adoption, in the science demonstration phase, which is basically the first 6 months where data are being collected, this data will be released immediately after processing. And so basically there is no proprietary period from the consortium. But also in the nominal science operation phase, the tier 1, so these are the data for the 1,000 planet with the first survey, they were public immediately after quality control is completed. Again, no proprietary period. And then for most of the other data are 6 month proprietary period, and it's only for a very small fraction, less than 10% of the data. And in particular, these are observation, the tier 4, that requires quite difficult to calibrate, and so we need a little bit more time in order to assure the quality control. But this is just to say that we have a very, very open approach. We believe it's extremely important to gauge the community early on in the analysis of the data, because at the end we really want to make sure that we can maximize the science return. So I believe my time is over, so let me wrap up to conclusions here. Exoplanet appears to be ubiquitous in our galaxy, and the number of discovered exoplanets is increasing exponentially. This is fantastic, but we still know very little about them. And I really believe that aerial will make a fantastic contribution to get really the first statistical chemical survey of exoplanets in the galaxy, because going for 1,000, so when so far we have been looking at a few tens, it will make a huge difference. The Aerial Consortium is very open, and we really welcome the participation of many scientists from these countries. We plan a meeting in the UK at the RAS when the RAS is open later this year, because we want to make sure that particularly the UK community is aware of the potentials and can join us. But even for people who do not want to join the consortium, but they're still interested in aerial, there are plenty of opportunities to engage with aerial, not only because they're very open data policy, but also because of all these citizen science activities and all the engagement that we're trying to have for ExoClock, the challenge, and many other things that didn't really have the time to cover today. So let me just finish by thanking you for this opportunity and looking forward to answer your questions if there are any.
Giovanna, thank you so much for a fantastic talk, and it was really great to hear about the upcoming aerial mission in lots of detail there. It's a very exciting future for the exoplanet field. So I think we've got a number of questions coming through, so I'm going to hand over to Sue.
Thanks, Emma. Yes, we've got some great questions. The first one is from Jeff Greenspan. Will Ariel be able to answer the question of how a particular exoplanet's atmospheric chemistry has changed over time?
That's an excellent question. Is a tricky one, because if you just have one object, so even if you know the objects in high level detail, it might not be really easy to disentangle some of the current characteristics, whether they were caused throughout the history of the planet but I think the great point of force of Ariel is the ability of not necessarily looking at just one object, but population of objects. And so maybe the degeneracy that we do expect when you're looking at one object in great level of detail might be addressed, because if you're seeing many of those objects and some of them will be similar, some will be very different, then it's through this comparison, comparative planetology, that we might be able to learn what might be due to one effect or the other. So this is what we're planning or expecting. Whether that is true or not, I think we shall see.
Great, thank you. Now I have a question from Keith Smith, who comments that it's a very exciting mission. There is a lot of debate about the cosmochemical origins of atmospheres on the terrestrial planets in the solar system, including Earth, where we have exquisite remote and in situ data, including things like isotopic measurements. How well can we hope to constrain the atmospheric origin of exoplanets based only on transit spectroscopy?
That's an excellent question, and to a degree is also linked with the previous one. If you just have a small number of objects, even if you have an incredible level of detail, like it happens for the planetary solar system, it's not granted that you can, go backward and understand what happened and why they are as they are. But the hope really is that if instead of having a few, you start to have hundreds, the hope is that we'll be able to see trends. And we hope to be able to learn from these trends. So for instance, I didn't see some of the simulations that we have been doing. Let's say that one see some correlation between the presence of one molecule and the temperature of the planet, or the presence of some other molecule and the type of star, and so on and so forth. If we're seeing this sort of correlation, if we're seeing this sort of trends, those will tell us probably something. And so that's where I think we might be able to learn something out of population of planets analyzed, not just individual planets.
Thank you. I have a slightly related question from Q Stanley here. How is observation bias mitigated with the data obtained in these exciting missions?
Well, certainly the fact that Ariel is using transit a technique is already a bias, because of course, if you're using transit, you're biased towards planets that are orbiting very close to the star, because otherwise the far away you are, the more impractical it is to use transit, because you need to wait too long in order to have another transit or another eclipse. So clearly there is a bias in this. But any technique has a bias. And so the idea is that at the moment you can do quite a lot with transit technique. But in the meantime, of course, I mentioned direct imaging and also other observations from the ground. Ideally, you really want to use all the techniques. So little by little, we will be able to address all these biases, both in the detection of planets, as you're probably remember in the diagram where we're looking at the parameter space, not all this parameter space has been covered yet. But by using different technique, you can little by little address these biases. And the same for hemispheres. Today we can do pretty well planets around that are orbiting close to the star. And when direct imaging will all evolve towards being able to look at even smaller planets and so on and so forth, then you will be able to do population analysis also with direct imaging, and so planets at larger distance. And so hopefully by combining all these techniques, we will have a better view with less and less biases.
Thank you. I have a question from Paul W., who wonders if Ariel will be capable of detecting artificial, i.e. non-natural chemicals or pollutants in atmospheres of exoplanets.
Well, I'm afraid that is, you need really a second generation of atmospheric observatories, because at that point, in particular, some of the species that have been considered that are in the Earth atmosphere, you need to have a very small concentration, so extremely small signals. So this is not something you can do with Ariel or even with James Webb, to be honest. And so we really need to think of next, or even the next one, generation of exoplanet atmosphere missions.
Thank you. I have a question from John Fairweather. Could Dr. Tinetti give an update, on the forthcoming exoplanet satellite Twinkle?
Yes.
What's happening with that?
Well, with pleasure. So Twinkle is well, first of all, Twinkle is a small satellite. We're talking about 45 centimeter satellites that will be launching in low orbit, and will be built by Airbus, also doing spectroscopic measurement in the optical and the infrared. But what is new about Twinkle is the funding model, because most space missions so far has been constructed with the funding coming from government organizations, so like European Space Agency or NASA or JAXA, is all government organization. This is fantastic, don't get me wrong, but most of the time these missions, like Ariel is such an example, are extremely ambitious, and because of that, they're also quite expensive. They take a long time to be built. And so it means that you can't necessarily have a mission like Ariel every few years or so. You need to wait a long time. And so we are at BSSL, which is the company that is managing Twinkle. We are looking into other possibilities, whether we can use some more a different business model, some more commercial model, in order to be able to fund more small mission and the data then can be accessed by the community paying a subscription. So it's a little bit like the sort of telecom type of model, but is using science data rather than telecom data, if it makes sense. And so this is the new model that we're trying to put forward for Twinkle. So at the moment is being studied by Airbus, who will provide the spacecraft.
Thank you. I have another question from Jeff Greenspan. What considerations went into choosing to construct the aerial telescope out of aluminium?
Well, that's an excellent question, and this was considered by the engineers that are behind the design of Ariel, because being aerial emission in the infrared, you don't want to have, well, the spacecraft will be mainly in aluminium, and so you really don't want to have a different material for the telescope and the rest of the spacecraft and the payload, because you want to have the thermal expansion and contraction to go together in order to have the least number possible of systematics. And so having a telescope, for instance, in silicon carbide, and then the rest of the spacecraft in aluminium would have not been a good match. And so that's where trying to match the material for the telescope and the rest of the spacecraft was one of the key requirements at the beginning.
Okay, thank you very much. Can you just remind us, we have a question from Paul W. again, wondering about detecting biospheres. I know that you said that atmospheric pollutants are going to be there in very small levels, but do we need to look at closer systems if we're going to have a chance of finding biospheres, or are there other constraints?
Well, I think, at least in my view, I think we still need to understand a little bit better what a biosignature could be. I mean, we are all extremely curious to see, in particular, first observation with James Webb or some of these small and cold planets like the TRAPPIST-1 that are potentially habitable environment. Of course, we don't know whether they are or not. But we still don't know exactly what to look for. Of course, people have put forward the idea to look for disequilibrium chemistry. This was the idea from Lovelock. So basically, the fact that life is creating some chemical disequilibria, and if you're able to look at some species, molecular species in the atmosphere that are completely out of equilibrium, this could be an indication that perhaps there is life in that planet, and that is a biosignature. For the Earth, the clear biosignature is molecular oxygen or even ozone, and they are in very high concentration because of the presence of life. But I think we all need to be a little bit careful when we will see all these planets and we'll have to interpret all these spectra. Even planets that for sure they're not habitable because they're very hot and maybe made of hydrogen, more gaseous. Many of the atmospheres that we're looking at, even with current instrumentations, seems to show a chemistry that is out of equilibrium. And so the question is, how we'll be able to distinguish what is out of equilibrium because of the chemistry or because of habitability. And so I think it is important, it will be important to learn, at least in my view, first, what planets look like in general. And hopefully at a certain point, we'll see some planets that really stands out, and perhaps the fact that stands out and they tick all the other boxes of habitability will tell us that, maybe this information is really a biosignature or so. But for the moment, it's very hard not to, perhaps not to think in a too geocentric way. So I'm just very cautious when it comes to biosignatures and habitability.
Thank you. And that's where we've run out of time for questions. So I'll hand back to you, Emma.
Thanks very much, Sue, for asking all of those questions. And thank you, Giovanna, for taking the time to answer all the questions. Lots of interest from our audience on your presentation. Thank you. So I'd just like to close the meeting then. So I would like to just thank once again our excellent speakers this afternoon. We've got messages coming through complimenting the fantastic talks. I wholeheartedly agree, really interesting talks this afternoon. So finally, we'd just like to give notice that the next monthly A&G open meeting of the Society will be on Friday, the 22nd of April 2022. So we have an extraordinary meeting on the 22nd of April. So thanks everybody very much for joining us this afternoon. I hope you've enjoyed it and look forward to seeing you all next time.